Business-wise, I saw that pretty much everybody managed to get their video introductions in, which is really cool. It was good to meet all of you virtually a little bit and see what everybody's kind of interested in, what people expect from this class, which I think, it seems like there's half and half, right? Half the people are very interested in how people have come to know the skies, and we'll do a fair amount of that, especially today, actually. But other people are interested in more of the kind of wild things we don't know about the sky, the black holes and the cosmological things. And for those people, you really have to sign up for next semester, because that's where we're going to be doing all that stuff. Did anybody have any general questions other people might want to hear about regarding the assignments or anything like that? Yeah.
What about the lab? Is there a certain day to do it, or like?
Yep. So the question is, when is the lab assignment due? All the assignments are due on Saturday night. You can turn them in late, those quizzes and lab assignments. They don't actually close. I think somewhere around the midterms, I'll close them out. And then I'll give you guys a heads up. I would not recommend putting them off. The video assignments I do grade every week. If you turn them in late, I'm going to take some points off because it's more work for me, and I want to incentivize you not to turn them in late, because then I have to be chasing people around and trying to grade their projects. It's much better for me to just do it all at once on Sundays or Mondays. So if you think of everything as being due on Saturday, I think it'll be a lot easier for you. Other questions? Okay, cool. So last time I didn't quite finish what I wanted to get through last time, and in general, I think this class might lag a little bit behind the textbooks and so forth, and I think that's for the better, because as we get into the back half of this course, we're going to be really exploring. We're going to be looking at all the different moons of the solar system in great detail, and what I found last year in teaching this course is that I probably should have spent less time on that and more time on some of the things at the front of this class, which are more generalized, because it occurs to me that most of you are probably not science majors, and perhaps this will be your only exposure. It's an intro astronomy class. Perhaps you would benefit more from a bigger examination of science as a whole and some contextualization than you would from the details of the 20th moon that we're going to talk about in this course. So, forgive me, but we will probably lag a little bit behind the actual Moodle and so forth. But stay up on it as much as you can, and come see me if you have questions about any of the material as you go through it. All right, so last time we talked a bit of, we mostly talked about these big ideas, like what is science, what are we actually trying to do in astronomy, and we're going to continue that to some extent today. I didn't really make it into our tour of the solar system, so I'm going to briefly go through the solar system today. But what I want you to start to envision is that science is a story that we tell ourselves. Now, we try to tell an objective story about our place in the universe, but that's very difficult. And of course, when it comes to astronomy, even more so than any other science, we don't have little test tubes and laboratories that we can experiment in. We have to interpret light, right? And, the material basis of light is still a complete enigma in modern physics. So we're working with a very shorthand here when it comes to understanding what's going on. So there's a lot of questions, and that's really exciting, because it makes a great example for how science is a progressive art form. And it is an art too, right? We're making some sort of creative storytelling process that integrates all of our best knowledge and tries to say something concrete about it to the best of our ability. Now, I wanted to start off today's class, if you'll bear with me. I want to read the foreword to this book. By the way, you guys should get this book. It's very good. It's called Native Science, and I'm going to keep referencing it throughout this course, because it provides a little bit of a nice balance to this very monolithic Western perspective of science that we're going to get from the textbook, which I think is super valuable, particularly technologically. But this is written by Leroy Littlebear, who is a professor at Harvard in the Native American studies there. And he's written this nice little foreword about what science means to in the indigenous tradition, which I think is actually quite revealing. So after I finish this, I'll take you on a little tour of our story of the solar system and the cosmos, and then we'll unpack that. We have to get into some nitty-gritties after that. Science has been and can be defined many different ways depending on who is doing the defining. But one thing is certain, is that science is culturally relative. In other words, what is considered science is dependent on the culture, worldview, and paradigm of the definer. Immanuel Kant, who divided knowledge into appearances, reality, and theory, suggests that the appearances of the world are deeply conditioned by the human sensory appearances and intellectual apparatus. Other beings no doubt experience the same world in radically different ways. Scientific facts, the appearances themselves, are as much a product of the observer's human nature as they are of the underlying reality. We see the world through a particularly human goggles. Now, we know this is true, actually. There's been some fantastic studies done where people are tasked with something like, say, we're going to ask you to count the number of people that come in and out of this elevator who are wearing white shirts, and you put all these people in a room and ask them to do this, and they play a video, people coming in and out of the elevator. And all of the students who are participating in this study, they get like $20 for pizza or something for doing it. So they all come in and do the study, and they're counting. And they have varying degrees of success at actually getting the correct number. And then afterwards, the experimenter says, did you notice anything weird while you were watching the video? And something like 70% of the people say, no, what are you talking about? And then the experimenter says, well, did you notice the giant gorilla standing in the room with them? Right? There's a guy with a gorilla suit who's in the elevator with these people. And only 30% of the people notice it, right? So depending on where your attention is focused determines largely your construction of the reality that you perceive. This is a very real human effect. Albert Einstein said that the business of science is reality. I agree, but the reality brought about by modern science is largely based on Western paradigms. Western paradigmatic views of science are largely about measurement using Western mathematics. But nature is not fundamentally mathematical. Mathematics is superimposed on nature like a grid and then examined from that framework. It is like the land survey program, a grid framework of townships, sectors, and acres superimposed on the land. These units in turn are used as the basis for dealing with the land, but they are not part of the nature of the land. Einstein was so enthralled with the mathematization of nature that he once observed, quote, "How can it be that mathematics, being a product of human thought which is independent of experience, is so admirably appropriate to the objects of reality?" But Jeremy Hayward, among others, feels that in spite of the usefulness of modern scientific discoveries, there's a lot left out of Western science. The modern world relies on a narrow, distorted view of science to attempt to relate what reality is all about. Quote, it is just that the modern description leaves out so much. It leaves out the sacredness, the livingness, the of the world. And it does get troublesome when scientists tell us, often with a voice of authority, that the part they leave out is really not there. If science is a search for reality, and if science is the search for knowledge at the leading edge of human knowability, then there are sciences other than Western science of measurement. One of these sciences is Native American science. Native American science is incomprehensible to most Westerners because it operates in a different paradigm. Measurement is part of Native American science, but it does not play the foundational role that it plays in the West. Measurement is only one of many factors considered. In order to appreciate and come to know in the Native American science way, one has to understand the culture, worldview, paradigm of the people. For Thomas Kuhn, the paradigm is a whole way of working, thinking, communicating, and perceiving with the mind. A paradigm includes tacit infrastructures, which are mostly unconscious, pervading the work and thought of a community. All right, let's pause there. So one thing that we're going to really have to clean out of our minds is that the story that we end up telling here today is the only story that can be told. Now, it's a very beautiful story, that of the solar system and the planets and gravity and Kepler's laws of motion and all of these nitty-gritties we'll get into. But it's far from the only way of looking at things, and in fact, there's a serious possibility that it neglects a great deal of reality because, for the most part, as soon as you guys leave the classroom today, you're not going to be too concerned with how the laws of gravity are affecting your daily life, but you are definitely going to be concerned with how it is that you're relating to the people in your lives. And so that's something that Western science has not had much success in rectifying and dealing with. All right. Now let's take a little tour of the Western cosmos. So just to remind you guys, distance and time are somewhat inseparable in astronomy. And this is convenience because we have found that light seems to travel at a constant speed in a vacuum or in a material. And so in order to cut down on the number size, the enormous length of the digits that we would need to describe the distances between these different bodies, we use the light year, right? And this is just the distance that is traveled in 1 year by light in a vacuum. Okay, so as you can see, it's, almost 10 trillion kilometers, and we'll get into parsecs in a little bit later, but it's an extraordinary distance, and it's, you can also think about a light year as something like out to about the edge of our solar system, depending on where you draw the line. There's a little cloud of bodies at the very, very edge, which is maybe a couple of light years away, called the Oort cloud, and we'll visit that in detail later. So there's this other unit that we use to measure within the solar system, which is quite useful too, which is called an AU, an astronomical unit. That's simply the distance between us and the sun. And you can see that an AU, you can see that a light year is about 63,000 AUs, okay? So here we are. This is where we're all standing right now. And this thing is about 13,000, this planet that we're on is about 13,000 kilometers across. There's the moon, and there's us. This is actually a 2-scale drawing of how far away the moon is, which might surprise you. It's actually a bit further than most people assume. So it's about 30 times our own diameter away from us, which is about 384,000 kilometers. So the moon's pretty far away, especially when you look at it this way. And there's a lot of extraordinary details to talk about our moon, and it seems to be a really important part of why we're able to be here on this planet. And we'll get into all of that soon enough. So light takes a few seconds to make its trip to the moon and back. That's quite interesting. So at some point back in the 70s, I believe, the NASA put a little mirror on the moon, and they can shine a laser off of it, and they can measure the travel distance this way. And that's going to play an interesting role in trying to understand what light is, and we'll talk about that briefly as well. Oh, well, let's say that. So the sun is this 1 AU away from us. That's about 150 million kilometers from us, which is about 11,500 Earth diameters away. So about 400 times the distance from the Earth to the moon. All right, now as we move away from the sun, if we start at the sun, we're going to find our nice rocky planets lined up in a row there. Mercury, of course, Venus, Earth, and we're going to go, after we make it through the basics here in the next week or two, we're going to actually start examining each one of these bodies with great depth, and we'll answer all of your questions about them then. But a brief tour. So we keep going, and look, out beyond the rocky bodies, we find this asteroid belt, which is an interesting puzzle, which we'll examine. What's it doing there? Is it the remains of something that's broken up? Is it left over from the formation of our solar system? Is it something else entirely? That's going to make a fun story. You go beyond that, you find Jupiter. You go beyond that, about 10 times the distance of us to the sun. You're going to find Saturn. Further out, you're going to find Uranus. Further out, all the way 30 times the distance of us to the sun, you find Neptune. Pluto's way out there, 40 AUs. And then beyond that, we get into all sorts of interesting little comets and what they call trans-Neptune objects, right? These are things that are not quite within the confines of what we traditionally define as a planet, which is somewhat arbitrary, and we'll talk about that. Maybe many of you have heard the news that Pluto lost its planet status, which is Just kind of shows you how arbitrary these lines are that we draw, right? And now there's talk, actually, I was just speaking with an astronomer a couple of weeks ago who was looking at the possibility of there being some pretty large planet-sized objects floating around out there in the Oort cloud, which is this thing that we'll get to, which is very, very far away. We're talking light, beyond a light year away from us, perhaps 2 light years away, almost to the edge of the next solar system. There's just this big haze of objects out there. Now, it's quite thin. They're not crashing into one another. There's thousands, hundreds of thousands of kilometers between these objects. But there might be other planet-like things out there too, which is really stirring up the way that we understand things. Now, I actually think that planetary science is a wonderful on-the-move discipline. And almost every day when I look at the science headlines, I see that planetary science is changing, especially with regard to how these bodies form, how stars form. The story that has ended up in your textbook and that ended up in my textbook when I took this class in college was one that was built primarily by studying our own solar system. So how we come to understand our solar system was how we thought all solar systems were. But it turns out that this couldn't be farther from the truth. In fact, almost no solar systems look anything like ours. Most of them are very homogeneous. They have one type of planet, maybe 2, right? Furthermore, one of the most common types of planets in the universe appears to be absolutely absent from our own solar system. And we'll talk about those planets. Just this morning I saw a headline that, actually still have it open over here, but the James Webb was checking out the Orion Nebula, and we're going to talk about Orion today. And they noticed that there's these strange planet-like objects, these Jupiter-sized planets, some smaller than Jupiter, that appear to be orbiting one another, right? So there's these pre-solar system bodies that don't make sense. They're not big enough to have condensed gravitationally under the traditional means that people use to describe how solar systems are formed. So what's up with that? And I have some ideas, and we'll really get into that at the proper points in this class. Okay, so there you have it. If you go thousands of AUs out, 10,000 AUs, 10,000 times the distance of us to the sun, remember, we're really far from the sun, you get to this Oort cloud business. And then a bit further, you're going to find our closest neighbor. So this is our solar system. And our solar system is nested in proximity to a number of other stars. And of course, we find ourselves in one arm of this galaxy, right? And of course, until about 100 years ago, we thought this galaxy was the entire universe because we couldn't see anything outside of it. And the things that we did see outside of it, we assumed were just little clouds of gas or something. They turned out to be a whole other galaxies full of trillions of stars. This just maybe give you a sense of how on the move this discipline is, right? Let me see, I actually wanted to play you this movie here and just give you a sense. We won't have to watch the whole thing, but I want to give you a sense of the path that our sun takes because our solar system itself is making its way through the galaxy. Now, most people have this conception that the galaxy is kind of a pinwheel and it spins as one object, but this actually isn't true. The solar system is making its way through each arm of the galaxy, right? This is actually a new revelation in science, and I think that it's playing into all sorts of discussions because how does it affect our life on Earth as we move through the arms of the galaxy? How are we interacting with more stars? Do we experience more cosmic rays? Does that affect our climate? Does that affect life on Earth? Probably. And in fact, there's some really interesting scientists working on this problem. One of them that I'll bring up later. So one thing that's really cool to notice about this is that as the solar system weaves its way through the galaxy, it makes this sort of bobbing motion up and down as it goes. It's also tracing out this beautiful braided path. And this isn't to scale at all, by the way. Of course, that sun's way too big. But it gives you a sense of the pattern of the motion of these bodies as they make their way through the solar system. So this very intricate braiding process is going on. And of course, all the stars with solar systems are doing the same thing. And there's this very intricate dance that's going on. So, our galaxy is also part of a local group of galaxies. There's more galaxies which we study. The closest ones are easier to study. The further ones are more difficult to study. And the James Webb is an update telescope to the Hubble, which was able to see with some clarity into the distance. James Webb has refined that. So the interesting thing that you'll find is that the word universe in astronomy probably doesn't mean what you mean by universe. When you say something like, there's nothing in the universe that could make me do this, or something like that, right? You probably mean nothing at all. But in astronomy, when we say universe, what we mean is what we can see. So the edge of the universe in astronomy is the edge of what we can see. These are completely inseparable concepts in astronomy. So it's very easy to be led astray into thinking that when we say the edge of the universe, we mean that's all there is. But we don't really have the authority to say that in astronomy. All we mean is that's what we can see. All right? And what's really interesting is that as we build these more powerful telescopes, we can see further and further and further. And so this plays heavily into the story that we tell, right? There's this story that's very popular in cosmology, and it has been for maybe 70 or 100 years almost now, of the Big Bang, which is this scientific version of the creation myth where there's a moment where everything comes into existence, right? And there's certain lines of evidence that were pursued across the 20th century in order to defend this idea. But what's really interesting is that as we've been able to see further with these new telescopes, well, with this new telescope in particular, the James Webb telescope, we see that our idea of what these early moments of the universe were supposed to look like don't appear as they should. There's fully formed galaxies a few 100 million years after this alleged moment of inception, right? So things are looking like they don't quite make sense anymore with this story, and the story's on the move as a result of it. And it'll be interesting, the further and further we're able to look when we make more powerful telescopes, what will we see at that point? Will it change? You know, I just, on the podcast, we just had this really interesting fella up in Ottawa. He's an astrophysicist, cosmologist up there named Gupta. And he's actually proposed that perhaps the universe is twice as old as we thought it was. And if it was twice as old as we thought it was, we would actually be able to explain the formation of these galaxies so that it would make sense there was fully mature galaxies, 13.5 billion years ago. So, nobody is seriously entertaining the idea that there was no beginning to everything, although that was the most popular idea prior to the 20th century. But you can see that the birthday is on the move, and that's how science goes, right? You have to update your understanding as you get new information. So that essentially concludes the 30,000-foot view of the modern story of cosmology, science, astronomy, right? Astronomy, we try to make physical explanation for the motion of the things we see in the sky. Science, we try to narrow down these possibilities as much as possible. And as you can see, the cosmos is huge, and there's so much left to be discovered about it. So what we're going to do now, and really this week in general, is we're going to have to begin to pick apart all the different ways of looking at it. And I'm going to try to do those in parallel. So, we have to come to understand the celestial sphere. This is the grid by which we've divided up the sky so that we can track the motion of these bodies. And we'll do that today. We're also going to spend a good deal of time today on ancient astronomy because it's kind of our last chance to really do that. As we move forward after this week, we're going to be looking with, exacting detail and great luxury of depth at each of these different bodies, each planet. We're going to look at the asteroids, we'll look at the comets. And we're not going to have a lot of time in those discussions to think about the ancients as much, although we will talk about them to some extent as we go through. And then I think we'll wrap up today talking about the difference between astronomy and astrology. Every year I have a student who sends me an email like, I'm really excited about this astrology class. And I'm like, all right, well, it's astronomy, but we can talk about that. So there's a misconception there, and I don't personally think astrology is rotten or anything like that, and I want to unpack the difference and what the two objectives of those different arts are, because I think they're very different. And we'll get into that hopefully if there's time today. Cool, and then I think next class we'll really get into the birth of modern astronomy and talk about a bit about the tools and the methods and how we've come to really make sense of the material nature of our solar system. So let's launch into it. Now, as far as I can tell, and as far back as history permits us to dive, people have been looking at the sky and they see a giant sphere over our heads, right? Now, this isn't wrong. I think I mentioned this last time. This isn't wrong, right? It's absolutely, from a relativistic standpoint, this is absolutely true. There definitely appears to be a sphere of objects passing over your head, you know? And actually, the most popular mathematical conception of the cosmos right now is general relativity. This is our description of gravity. And it's a very relativistic way of looking at the universe. So, you know, I want you to consider that the way that we chop it up has persisted into modernity. The way that we talk, the reason that the celestial sphere is even in your textbook is because this is exactly how astronomers chart the sky to this day. So there's something valid about that, despite the fact that we now know that the Earth is turning, and that's why the skies appear to revolve around us, right? Both things can be simultaneously true, and I think there's a lot that we need to be able to master in terms of being able to hold two opposing perspectives in our mind at the same time when we consider the story of how we come to know the universe. It's a lot more difficult than the simple headlines might have you believe. You know, I think we do a great deal of disservice to ourselves when we talk about science as being this monolithic, here's how things work way of approaching the world. It's really not like that at all. There's multiple ways of looking at how things work, actually. And by studying more of them, by integrating more possible descriptions of nature, we can maybe arrive at something closer to the truth. And of course, that's what we're really after. We really are after the truth. Because ultimately, look, how do we make decisions in the modern world? How do politicians make decisions? Well, increasingly, they're turning to the scientists to tell them what the heck's going on, right? So it's not some trivial pursuit necessarily, right? If the science is thought of as this one answer, as opposed to this plurality of possibilities that can be narrowed down gradually, then we run the risk of chasing some falsehood, right? Some non-truth, and making decisions that will greatly impact our survival on this planet. Or not even necessarily our survival, but our thrival, let's say, to coin a phrase, right? Our ability to thrive in this world. And so it matters a lot. Anyways, right above your head, when you look up, is called your zenith, okay? And you have 180 degrees, assuming you're standing without any mountains blocking your view or anything, out to the horizon, which is at the edge. And so the technical term for the edge of this celestial sphere from your viewpoint is the horizon. So that should come as no surprise. Now, the celestial sphere itself appears to rotate above your head along the north-south polar axis. So what does that mean? It means that if you are standing somewhere, so this actually is taken from somewhere down southern hemisphere, and this person is looking down at the south pole star, actually. This is where everything appears to rotate around it, okay? Now, this is kind of cool, actually. So you can actually, if you take a time-lapse video of the night sky and you point it at, in our case, the North Pole, you'll see the same thing. And what's really interesting is that if you can find the North Pole star, and I'll show you how to do that in a minute, you can determine your latitude on Earth anywhere you are. And this has been known for thousands of years, actually. In fact, navigating the ocean requires that, in some sense, you know your latitude and longitude. Latitude's really easy to find according to this method, because all you're really looking at is your elevation to the pole star from the horizon, the number of degrees that the pole star is lifted above the horizon. That's your latitude. So you can figure it out anywhere you are on Earth, essentially. It's quite easy to do, and I'll show you a quick way to use your hands to do that in a second. Longitude's a lot trickier, though, right? Because longitude requires that you understand how fast you're moving away from some arbitrary meridian. And understanding how fast you're moving means you need to be able to keep time, right? Because distance can be deconvolved from speed if you know how long you've been traveling. Sort of like how we use light years to get distance, right? This has been the perennial problem for navigators for thousands of years. They were always trying to come up with new ways to clock what was going on, and it was very tricky. And so some of the big leaps in technology came from the search for clocks, actually. And Galileo was involved in these, and many of our other early thinkers that we'll talk about in this course. So what do you think that the celestial sphere looks like if you're standing at the equator? Anybody? Wild guess? Yeah?
Just a straight line? Like everything's a straight line?
Yeah, basically everything, this thing is going to be moved down, and you're going to just see half of that circle, right? The cool thing is, if you look in either direction, you're going to see the exact same thing. You'll see the southern sphere, and you'll see the northern sphere. So I think I got a picture of that. Yeah, it looks something like this. Oops. Something like that in either direction, which is pretty cool. All right, so this is just a schematization of the same thing from your textbook. You can see that if you're standing there on the equator with the zenith directly above you, you're going to be able to see both poles, right? If you're at the North Pole, you're just going to see the celestial sphere going straight around your head. So the really cool thing, this is what I'm trying to get you to comprehend, and I want you guys to try this out if you can bring yourselves to identify the North Pole, the pole star, and I'll show you how to do that, is that you can calculate your latitude anywhere you go. And it's really fun to do. If you travel like up and down the coast like I do, you can actually check this out and see how good you are at estimating it, right? So here we are in Ashland. We're about 42 degrees, right? And you might say, well, how do I figure that out? So nice little rule of thumb is that your pinky is about 1 degree of separation, right? And remember, we're talking about 180 degrees in the sky, okay? So your pinky, if you hold it up and you actually count pinkies, now you could speed that up a bit, right? You can outstretch your hands and get about 25 degrees like this, with your thumb and your pinky. So you can kind of find your way and see if you can do it tonight. You probably won't be able to see any stars tonight. But one of these nights soon, we're going to get some clear skies and see if you can do it. Of course, the trick is going to be locating that pole star, and I'll show you how to do that. We'll talk about that. The moon's also pretty constant. You can get a sense of that as well if you're looking at the sky and you see the moon in it. The moon's about 1/2 degree, so you can use that for some measure. The sun. The sun. Well, something else about the moon, too. The moon is shifting in its place, right? And this is another thing that's going to help us with time. The sun is also shifting in place. The sun moves from where it rises each day by about 1 degree. So if you note that, then you can get a sense of this expanse of the sky. I think it's worth also mentioning about the sun. I think about this in the morning sometimes. So the Navajo have this tradition that you have to get up before the sun rises, because if you don't, you're going to make the sun waste its energy on waking you up, which, it might seem a little silly or something, but that's an interesting cosmological approach to the universe, where instead of the universe working for you, you actually have to work for it at the same time. I think there's something very productive about that. We live in a world where we've mastered the nucleus, right? We can split atoms. We can develop these incredible computer technologies, but they also at the same time threaten our well-being in a way that is somewhat one-sided. It's almost like we master the universe, and we create all of these landmines for ourselves and then kind of shrug our shoulders about how that happened. And I think there's something really valuable about some of these more ancient or indigenous traditions that seem to be very aware of those pitfalls and how these things can happen if you're not careful to integrate the idea that there is some responsibility of yourself to everything else, including the sky. And, it might not be objectively true in the material sense, but it does seem to be metaphysically true in that it does play out that if you don't actually take concern for your surroundings, they will do you in eventually. All right. Now, we've talked, I don't know if we mentioned it last time, but there's essentially a plane, kind of thick, squishy pancake upon which all of this plays out in our solar system. So you might have noticed all of the planets happen to be more or less in the same plane. And the way that we chop up that plane is we use these constellations. So that plane is that dish, the platform upon which everything plays out, is called the ecliptic. And it's actually has some thickness to it, right? It's about 18 degrees. So not all the planets and bodies are in exactly the same place, but they are more or less in the same place. And the way we divide it up is with these constellations, okay? So again, this has persisted into modern astronomical sciences. If you want to tell me where a star that I'm supposed to be looking for is, you're going to tell me that it's in the constellation blah, whatever. Or it'll tell me it's between these two constellations, and that's where I should begin looking. Or it is this many minutes of arc to the right of this constellation. So these mythologies have persisted into the present, and I don't think it's an accident. And we'll talk about at least one of those today. And you might ask yourself also, why in the world are all of the planets in a plane like this? This is a question I've been asking since I was like 10 years old. Anybody else ask this question? No? All right, I'm just a weirdo. So it's actually quite perplexing. And if you had asked, say, a professor in my position when I was in college, they would probably tell you, well, that's because when solar systems form, they are essentially dissipating this angular momentum. So they're spinning, and if you spin, essentially, you could try it right now, but you'd probably hit your neighbor, but your arms will fly out to the side, essentially. And this is a matter of conservation of angular momentum, to use a very bulky scientific word. But essentially, this is a natural process of spinning systems. This is all well and good, but there's things about that are contraindicative. There's parts of that explanation that just don't sit too well with myself and with many people. In particular, there's certain rotational dynamics within our solar system that aren't homogeneous. Venus is spinning the wrong way. There's a number of moon systems that are spinning the wrong way. There's a number of things that planets are tilted on their axes in different ways. There's a number of little pieces that suggest a much more rich and varied history to this solar system than the simplified version might have us believe. And of course, one thing that's really exciting to me is that scientists are now studying how the sun, which is this wildly electromagnetically active body, shapes this wider thing they call the heliosphere, which is essentially this big, let's say, blanket, very organized blanket of charged material, right? Very fast charged, electrified ions that are flying away from it in the solar wind, and how those processes, in some sense, reinforce this plane, right? Now, the details of how that plays out into organizing the solar system are absolutely at the cutting edge of science. But it's a really, really fascinating topic. So if you're interested in that idea, I recommend you read about it. There's this gentleman that I had this pleasure to speak with this summer. So this is my friend Eric. He's an astronomer at Princeton, and he's looking at how exactly the helios sheath, this blanket of material that's flying off the sun, how it organizes things really far away, how it organizes the motion of the planets and everything else. So I put a link to this in your Moodle, and you can check it out. It's kind of a long podcast, but maybe you watch just a little bit of it and get some ideas for where that research is headed. Because ultimately, these heliospheres, they can also maybe explain some bigger problems for us too, like how is it that our star system interacts with the star system next to it? Does it? Is that important? Because if you look at that Oort cloud diagram that I showed you earlier, the edge of our solar system is essentially right at the edge of the next solar system. So the solar systems are pretty tightly packed. They're actually bumping up against one another. Now, that doesn't mean they're necessarily grinding into one another, but the effects of these different streams can't be ignored. There's something there, and it's just at the edge of what people are even starting to think about, right? Again, 100 years ago, we thought that the galaxy was everything in existence, right? We thought that the solar system that we were living in was the same as every other solar system. We had no idea about this Oort cloud. We had no idea that our solar system was extending light years out from where our sun is. So there's so much new information coming into the picture. All right, so we talked about the seasons last time. I don't think I need to go into that too much. Of course, I guess it's worth reinforcing the commonly held myth, and this might be something you can go tell your friends about. Look, you are not actually closer in terms of your orbit to the sun at wintertime. So further. So this winter, on the solstice, we will actually be at our closest point to the sun in our orbit, not the furthest, which is, I think, confusing to most people who don't understand exactly how the seasons work. And again, the seasons work because of the tilt of the Earth. Essentially, you're staying tilted the same way as you make your way around the solar system on this planet. And at some point, you're facing the sun in the northern hemisphere, and at some point, you're facing away from the sun at the northern hemisphere. And there's a lot of effects of how that plays out, and we'll look at that. It's not so simple as the amount of sunlight, although that's part of it. It has to do with the angle of the rays and so much more. Okay? So remember, this winter, when it's really cold, you're actually going to be closer to the sun in your orbit than you are in the summer. Now, it's of course the opposite for people in the southern hemisphere. So it's kind of cool. All right, so the ancients called the planets the wandering stars. Does anybody have any idea why they said that? Yes? With respect to the other stars, exactly. Yeah, they moved around with respect to the other stars. So people have been watching the sky forever, and they noticed that there's these certain stars, right? Because they look like stars, let's be honest. If you've ever gone out, and I encourage you to go out, you can get a little app on your phone that'll tell you what the stars are. And look at them, go find Jupiter in the sky. Go find Saturn. I think Saturn's out. I saw Saturn last week. Mars is out. They look like stars, right? But what you'll notice if you track their position from day to day is that they're not in the same place every day. And all the other stars seem to be. Now, there's even more perplexing aspects to this. Like, some of these wandering stars appear to go backwards at some point in the year. Now, this was really, really strange to the ancients, okay? And as you can imagine, if there appears to be stars that are just kind of doing their own thing while everybody else is marching lockstep, there must be something special about those. And so they symbolized their gods in these stars, right? So Mars is, of course, the god of war to the Romans. And there's a long tradition of Mars being associated, because it's red, right? You talk about like seeing red and being angry, right? And this is a very real, there's something very, very visceral about the color red that we associate with anger and rage. And so the Romans used Mars for that. But, we still think of the world this way. If you think about the days of the week, why do we have 7 days in a week? And why do they have the names that they have? It's very perplexing, actually. There's so many of these things that we operate under in our world that we just take for granted. We've just inherited these traditions, and we don't know why anymore. But actually, all of those days are named after some of these celestial bodies, because this is, of course, how people organize their lives in the first place. So think about Sunday. That's an easy one, right? Sun. What about Monday? That's the moon day. Tuesday is interesting. So you have to Latinize it, which is like, in Spanish, it would be Martes, right? That's Mars for Tuesday. Wednesday actually comes from Norse, which is Woden's day, which is one of their supreme deities. Wednesday, Latinized, in Spanish, it's Miércoles. This is Mercury's day. Thursday is also Latinized Jueves, which is Jupiter. Friday, from the Norse, Freya. This is the god of love and beauty. And then, actually the Latinized version of that in Spanish, Viernes, is Venus. And then Saturday, of course, that's easy, that's Saturn. So it's kind of fascinating when you look at Western culture today and Western language and so forth, and you think about what it is that, out here in America we have integrated into our language and into our symbolism and stuff. And it seems to be a nice mishmash of this Greco-Roman Mesopotamian tradition mixed up with a lot of Indo-European mythology, right? That's how we get all this North stuff that came into it. And of course, many of you might not realize this, but this country was essentially a bunch of English rebels, aristocrats who founded this country. They didn't like the king, right? But where did the English come from? Well, the English aristocracy that gave rise to our nation here, they were actually conquerors from the Nordic areas of Europe, right? From around the Netherlands and so forth, right? This was the Saxon invasion of England. Actually, the indigenous British people were all but eradicated. And you can find some traces of indigenous British people out at the edges. If you go to Wales or you go to Scotland or Ireland, they actually speak a different language there, right? They speak this Gaelic tongue, which is indigenous. But the people who actually were their native indigenous people were almost entirely driven out. So this tradition does bring us back to the Norse and those conquering Norse people who came in and actually moved through England, eventually brought their traditions to us here in America. So we have this nice mismatch of Roman and Greek traditions. And actually, if you don't think that we're essentially Rome version 2.0, all you have to do is look at, what is the language that all of our laws are written in? They're written in Latin, right? This is the Roman tongue. All of our medical textbooks, medical terminology is written in Latin. Our state houses, our courthouses, they all have Roman Greek architecture. This isn't an accident, right? This is because we're essentially continuing that same tradition to this day. So, people talk about how the fall of the Roman Empire and stuff, but it didn't really fall, right? It just sort of changed forms. All right, lost my pen. Ah! All right, so I want to take a look at, and in your textbook takes a look at one constellation in particular, which is one that it's probably the easiest one to see in the sky, which is Orion. Now, last time we took a little peek at some tens of thousands of years old artwork that we found in caves, that we found carved on the back of these bone tusks. And people were also looking at Orion. And it looked a little different back then because things changed position. But it's proved to be a really important marker and also a really important vehicle for telling stories about the world. And, there's something that I want to talk about, which is one thing that's happening in Orion right now, which I think we should be aware of, which is this little star up here. And it's going to give us a chance to maybe introduce the scientific concept of magnitude and brightness, which will prove important as we go through this course. So that little, well, it's not so little, the sort of big reddish star that's up there is an interesting star. It's called Betelgeuse. Now, Betelgeuse, maybe you get a better look at it up there in the upper, I guess your upper left-hand corner. This is an interesting planet because it seems to be changing in brightness, right? And this is, for the last few years, has been a topic amongst astronomers of why it's doing that. And there's been lots of different hypotheses for why it has been doing so, but it appears to have been doing so for quite some time. So here's a picture of it between January 2019 and December 2019. And you can see that even in those I guess that's only 1 month, right? No, January, that's almost a year, right? But it's changed in brightness considerably. So it changed over that time period, let's see, from about magnitude 0.5 to magnitude 1.7. So what the heck is magnitude? Magnitude is the way that we measure the brightness of these bodies in the sky. Now, I think it's important to familiarize yourself with magnitude, but it's not a simple magnitude 2 is twice as bright as magnitude 1. It's actually a bit unfortunate how this came about, and it's perhaps telling of how we integrate old ideas into new ones, and sometimes we move forward with old ideas that we probably should have just wiped the chalkboard and started over with. But in this case, what happened was this very famous Hellenistic Egyptian astronomer named Ptolemy, who we'll talk about next week, created one of the most robust star catalogs. He inherited a lot of data from the Sumerians and from the Egyptians, but he started to inventory how bright the different objects were in the sky. And he ranked all of the stars that he could find from first magnitude to sixth magnitude. First magnitude being the brightest, sixth being the dimmest. And so when we actually started to have the technology in the 20th century, photo multipliers and different ways of really taking photographs and comparing the actual brightness of stars, we still had 1,000, 2,000 years of observations of brightness that we wanted to still maintain. And so we tried very desperately to map our new understanding of brightness onto this Ptolemaic system of brightness, which was somewhat arbitrary. So in the modern system of magnitude, the reality is that a first magnitude star is actually 100 times as bright as a sixth magnitude star. And there's a sort of complicated mathematical formula that you can use to calculate the amount of brightness that increases. But what's important for you to understand is that it's not this simple linear scale. It's actually logarithmic. And I believe it's a fifth root that's used to determine it. So looking at our own celestial sphere here, we see a large range of different magnitudes. And it gets really, really preposterous in some sense because at some point, the planets, particularly Venus, is more bright than a magnitude 1 star, right? So they put a negative sign in front of it. So Venus is actually magnitude negative 4.2, and the Sirius, which is the brightest star, technically, in the sky, is actually a minus 1.4, something like that, 1.5. The sun, for instance, is magnitude minus 27, all right? And some of those images that we see in those Hubble Deep Field images, maybe you've seen some where there's just galaxies all over the place. Some of those are as dim as 30, plus 30, right? And of course, remember, this is logarithmic, so those are hundreds, perhaps thousands of times more dim than something which is close by. And it explains also why these things that are so dim were completely unacknowledged by astronomers until very recently, in the last 100 years. This is why we thought that the galaxy was it. But I want to talk about one particular apparition, let's say, a piece of a constellation, which is very important, right? And you guys have seen this one before. Maybe someone pointed it out to you once or twice. This is the Big Dipper, right? Well, this is actually a Van Gogh painting. But it's proved really important. Now, why is it so important? It's important because it helps us locate that pole star upon which the entire celestial sphere appears to rotate. And so people have been paying attention to this one more than any other, at least in the northern hemisphere, more than any others. And I'm mostly going to concern myself with the northern hemisphere in this class. So if anybody, by the way, I record all these lectures to YouTube, so there are probably some people listening down under, and I apologize to them. But, in the southern hemisphere, they have their own version of that. They have the Southern Cross, which is quite useful. But in our case, this is the one that we're obsessed with. Now, the Big Dipper itself doesn't contain the pole star, but it is very easy to see. It's much easier to see than its companion, which is this Little Dipper. But if you can see this dipper, and you can see where the edge of it, the little tip of this bowl is pointing, then you can find that it's pointed at the handle of the Little Dipper, which will tell you where your pole star is. If you can find that pole star, then you can find your latitude. Then you know exactly how far up and down you are on this coast or whatever, right? This can be quite useful for navigation, especially in the absence of anything else. It can also allow you to find which way is north, right? If you find yourself stuck in a forest somewhere, right? You have no compass. Well, if you can find that pole star and you just keep walking in one direction or the other, you'll eventually hit something useful, I promise. Another good idea is to find a river and follow that. It'll take you somewhere productive. All right, so check it out. Next time the stars come out, see if you can find it. See if you can calculate using your hands your latitude position. And it's a good party trick. You can impress your friends. Maybe it'll save your life one day. All right, so the Big Dipper is not actually a constellation, though. Neither is the Little Dipper. So we have these things that are in between, right? The constellations are these very specific, there's 88 of them. We use them to divide up the ecliptic so that we can navigate where we're looking with our telescopes. That's something very specific, these constellations. Among the constellations are even smaller images, and we call those things asterisms. So the dippers are actually asterisms. And the asterisms that are associated with them, I want to unpack a little bit. And this is probably going to take some time to do this. But I think it's quite interesting. So people have been telling stories in multiple cultures about these bears in the skies associated with these particular dippers. Now, if you squint, you can see maybe there's a bear there. I don't know. I don't really see a bear, but for some reason, people are always seeing bears up there, right? And there's, I think, 3 different Native American traditions that invoke the bear, and of course, the whole Greco-Roman tradition invokes the story of the bear. So what I want you to do as I tell you this story this morning is I want you to think deeply about why it is that the people chose this story that I'm going to tell you. Why is it so significant that it keeps cropping up in different cultures, or that it persists over thousands of years up to the present? And to that end, I think that there's a really healthy practice that I want to encourage everybody to do. You guys probably watch shows, series, stream stuff, watch Netflix, whatever, go to the movies, right? Do you guys come out of a movie, do you watch movies with your friends or with your partner or whatever? Do you just go to sleep afterwards, or do you try to talk about what it meant to you? I hope that you guys do that. So I do an extraordinary amount of that. You know, my wife and I will watch a movie, and then we'll spend the next day or something like trying to unpack exactly how those characters' actions play out in our own lives, actually, is what it really comes down to. Oh, I know a guy that's like that, right? I've seen this struggle play out before. And I think what has happened is that there's something so absolutely typical about the experiences that we encounter that they have been formalized and concretized in the story that these ancient people have encoded in the sky. So let's look at this story. And this bear in particular is called Ursa Major, which just means big bear, all right, in Latin, which is the Roman tradition. And there's an interesting story here in the West. And what's interesting about this story is not simply the story that I'm going to tell you at first, but how it was sort of transmogrified, sort of bent into a new story that reflected the culture of the new people. So the story that we'll start with today, although I think there's earlier editions of it, we're going to start with the story in ancient Greece, right? Now, ancient Greece, you have to understand, really started with the Minoan people. Now, the Minoan people are really fascinating because we don't know much about them because their entire civilization was obliterated by a volcano somewhere around 1200 BC. But it seems like the Greeks really worshipped these people and wanted to be like them and inherited a lot of their linguistic traditions and a lot of their mythology from these people. Now, the Minoans, unlike, say, the Romans, were a matriarchal society. We don't see any real matriarchal societies on Earth today, but this is really fascinating. It seems like the rulers were women, actually. And if you, and we'll talk about this more in a little bit, but I want you to consider that the inception of this story was in a matriarchal society, and later when we see the Roman version, it was a deeply patriarchal society. And I don't mean that in the sense of like the patriarchy and the tyranny and so forth. I just mean that there was a more masculine bent on the society by the time of the Romans than there was in the ancient Greek times. And that transition happened over 1,000 years. So the Greek version, which I believe was in some sense, I think there's reason to believe was inherited in some sense from their ancestors, the Minoans, went a little bit like this. These are the main players. So Zeus is kind of the father deity in this story. Hera is his consort, the mother deity. There's these deities that inhabit the earth, right, that embody the earth. In principle, there's Artemis, who's kind of the goddess of the woods and nature and earth. And she's flanked by these nymphs, right? She has all these creatures of the woods. And they're very beautiful. And one of them is named Callisto. And we'll talk about Arcas in a second. Now, the story goes like this. Zeus became enamored with one of these little forest creatures, these nymphs, right? Very beautiful. But all of these forest creatures had pledged allegiance to Artemis, the overarching forest deity, and they were all virginal, right? So Zeus had this, very powerful sexual attraction to Callisto, and he decided he was going to get what he wanted, right? So the way that he did that was he changed himself into, he deceived the nymph by making himself look like Diana, and, I keep mixing up the Roman, Artemis. In Roman, that's Diana. So he masks himself as Artemis and goes and essentially, copulates with the nymph. And at the last minute, when it's too late, the nymph realizes what's happening. She realizes she's been deceived, and it's too late. The deed's already been done. And of course, this is a real tragedy because, you can't be a nymph if you're not a virginal nymph, right? They're these pure entities who haven't been soiled by earthly pleasures and all of these things. So she's in real trouble now. And the story goes in ancient Greece that the master of the forest, Artemis, throws Callisto out of the party, let's say. She turns her into a bear, all right? Now, what's really tragic about this is that she has a son as a result of being impregnated by Zeus. The son, Arcas, turns out to be a master hunter. Now, if you know anything about hunting, bears are sort of the supreme, object, right? They're very difficult to hunt if you're a hunter. They're very dangerous. Actually, bears are some of the most dangerous animals. You can see this. They actually did some experiments before there was animal cruelty laws and so forth. They put bears in cages with, lions and tigers, and it's like no contest, right? The bear just wipes out the tiger in like one stroke of its arm, right? So bears are this sort of archetypical predator, right? So in some sense, Diana does her a favor by making her the most powerful of the beasts, but at the other time, she's now constantly susceptible to being killed by her own son, right? And this is sort of, in some sense, embodying the shame of the intergenerational shame of having betrayed the earth in the first place. Okay, so what does this actually mean? And, I'll give you some of my ideas, but I don't think that there's any one meaning. I think that the reason that people tell this story is because it's so rich with meaning that you can't actually ever stop coming up with new meanings for what all of these pieces could represent. And actually, if you look at what are some of the most famous stories that we have today, like what are the most successful ones, I think? When I was a kid, maybe it was Star Wars. Maybe Harry Potter, right? Lord of the Rings, right? And these are popular because, in some sense, they're so rich, they're overflowing with meaning. Each one of the actions of the heroes and the villains seems to play out in the daily world amongst crooked politicians or amongst murderers and amongst people betraying their best friends, right? These things happen over and over and over again. So in this story, it's kind of interesting. In some sense, it's an archetypical story about deceit, right? It's sort of a cautionary tale, like, hey, things aren't always as they seem, be careful, right? Because, of course, Callisto was deceived into thinking that Zeus was actually this nymph's trusted companion, right? I actually left out one piece of the story too, which is that at the end of all of this, Zeus sort of takes pity on the mess that he's created, and he rescues the bear and puts it in the sky, right? So that it can't be hunted by her son. And so there's a redemptive aspect to that as well. There's also this interesting story of how the father deity, let's say the illuminating force, the seeker of knowledge, wants to know the earth really badly. And I think this is probably the more appropriate and correct interpretation of this myth. humans, right? We have this part of us that really wants to know how things work. We really want to be able to manipulate our environments, right? We want to be able to send rockets to space. We want to be able to build iPhones. But with that great knowledge comes great responsibility, right? There's really a lot of disasters that can come from sticking your head into things and tearing them apart and harnessing the knowledge, but not being entirely aware of the second, third order effects of it, right? I mean, this is playing out huge in this climate change narrative that's going around right now, which was not something that was talked about when I was your age at all. But right now, it seems to be that this is the central fixation of humans. When I was a kid, everybody was just so freaking excited to have invented all of these technologies. There's 2 cars in every drive, right? You know, I was just really excited to get my driver's license and be able to just drive around, right? I remember just driving for fun was a thing we did when I was a kid, right? We listened to music, just drive, right? Which is kind of, I think, totally morally inappropriate in our current cultural landscape. But the fact of the matter is, this is kind of what humans do. We figure out stuff, and we get so fixated, target fixated on what we can do and how we can apply the knowledge that we have, that we sometimes neglect the second and third order effects. And I wonder if there isn't some cautionary tale from our ancestors in there about that. Anyways, think about it. I would love to hear other interpretations if you guys can think of any. But more importantly, I want you guys to try to put that kind of lens on stories when you hear them throughout the day, or when you go and you relax at night and watch a movie or something like that. Think about the meaning of it. Think about the meta-level meaning. Think about how those characters play out in your own lives, and think about what the overarching meaning of those things are. Talk about it with your friends. So now the Romans changed things a bit. So these are the Minoan oligarchs, right? These are the matriarchs of the Minoan civilization. It's quite interesting. The Minoans' dress is really quite striking, right? The women, they bore their breasts in public, which is quite unimaginable in our Western society today, right? But this was a sign of strength for those oligarchs in that time. So it was a deeply matriarchal society. The women were in charge, for sure. And it's unclear exactly the details of how that worked out and how their armies were organized and so forth. Like I said, they were wiped out by a volcano. Now, here's how the Romans changed it, which is quite poignant. So the Romans took that exact same story and they changed one little key piece. So instead of the earth deity being upset at having been essentially betrayed by her nymph, they made it the jealous wife of Zeus who became enraged. So you already see this hint of setting up a power hierarchy with the feminine deity being, in some sense, spiteful, jealous, enraged. There's a tinge of something that you didn't have in the Greek domain. And I think this is really, really important because I think as we watch these myths and these stories change over time, look at how the heroes of our own stories reflect how we think about those people in society. I think that's what was happening in the Roman times, right? And of course, we're in this great pendulum of change with that, right? The concept of equality between the sexes is something that's actually relatively recent, hasn't been seen for thousands of years, but that's something that's making a huge comeback today, at least in promise, right? So, women couldn't open bank accounts until the 1970s in America. Did you know that? It's pretty crazy, right? Most colleges didn't accept women until the mid-20th century, and I'd say most of them not until the 70s or 80s, right? That's wild. So there's really been like one generation of women, let's say your parents, who really even had the opportunity to participate in the intellectual sphere the way that men had been doing for centuries before that. So we're at this moment of inflection where we've been kind of backtracking on this Roman idea of how society should be organized. The women in Rome had absolutely no place in politics or decision-making about how the future unfolded. And I think their mythology reflects that, right? I think that they've encoded that belief into this story, right? They fundamentally, and I hate to say this, but it seems to me that they fundamentally perceived women as spiteful, jealous, and envious, and these things which they wanted to keep in check to some extent. I think that those are misconceptions. And of course, you always have the interplay of different power dynamics and people wanting to assert themselves in different groups and so forth. So we're actually in a very beautiful and privileged spot, I think, in the world today because we have the ability to step back from a lot of these traditions and look at them. Now, that's also a really dangerous position to be in as well. I don't think that it's as simple as throwing away all of our traditions and thinking that they're all useless at the same time. That gets us into a wholly different disaster. The Native Americans have a few different bear myths as well. I don't have time to go through these, but I want to just show you a few different instances of how people have looked at this same apparition in the sky and come up with totally different ideas that reflect their own culture. So the Iroquois have these 3 hunters pursuing the bear. Lakota have the great bear. The Algonquin have the bear. The Navajo see these the dippers as something completely separate, and I don't have time to, there's a nice passage in here, maybe we'll get to later, about the revolvers, right? And that makes sense, calling them the revolvers, because they do seem to move about one point. And it's all about moving around this central fire and how basically their ceremonial acknowledgement of this process, of that wheel, is important in keeping the world held together. And I think that there's actually some really interesting physics there in terms of how the different bodies are connected to one another that is very prescient, but we don't have time for that right now. Each culture is a little bit different. So in India, they see not a Big Dipper, but they see the 7 sages. And in the Vedic tradition of India, the sages are each kind of like their own pantheon. Like each one of them is almost like its own prophet. Each sage has a number of stories and fables and parables that are associated with them, which I don't have time to get into today. But this is, of course, something like a nativity of all of the different deities in which they can, or prophets by which they can learn from. In China and Japan, you have the pole star being a god of war, and there's a number of stories associated with that. In Korea, you have the 7 stars of the north, and there's this very, very interesting story that I encourage you to look up later. I don't have time for it, unfortunately, today, but it essentially involves the betrayal and deceit of an old widower and how her sons come to rescue her from this crisis. In Finland, you have people seeing in the sky a salmon weir. Does anybody even know what a salmon weir is? Right? You do. Nice. Yeah, it's a little trap, right? So you can catch salmon. You sort of funnel them through these sticks and you can spear them, right? In Burma, you have a lobster in the sky in the place of the dipper. So each culture is going to make the stories relevant to itself, to its people. But ultimately, they're still telling these tales of what can go wrong when people don't take responsibility for the second and third order effects of their actions. There's something very, very similar about all of these. And we'll talk more as we get into the individual planets about how unbelievably similar some of those stories are by totally removed, geographically removed peoples who come up with very similar stories for each of these bodies. And that's going to be really fascinating to look at. So the last thing I wanted to touch on today is the difference between astronomy and astrology. Remember, astronomy literally means the laws of the stars, the laws of the motion that the stars go through. Astrology, logi being the study of, is really a study of the meaning of the positions of those stars, right? And arguably, both of these pursuits are about as old as one another from what I can tell. People have been trying to divine meaning from the stars, which is closer to this mythological pursuit that we've been talking about, as much as they've been tracking the predictable regular motions of those stars. So both of these things come into play in human history. And in all honesty, I encourage you can read the astrology in the local newspaper or whatever. It's usually quite useful advice. It's usually something like, be careful, don't do anything stupid today, something like that. So I don't think there's anything wrong with that. Now, it hasn't held up to the test of being able to make predictable statements, right? I mean, a good way to see this is that you look at the astrology report in one newspaper, and on the other side of the country you get a report that contradicts it. On the East Coast, in some newspaper, it will say, don't go outside tonight, and on the West Coast it says, go outside tonight, right? So there's a lot of self-contradictions to it. But I think in general, it's trying to get you to think about orienting yourself with some meaning throughout the day, which I think is actually a really productive practice. And people in astrology, in the astrology community, will often make the argument that, hey, it seems like rationally that where you were born should matter, right? Because, assuming that all of the stars, all of the planets are gravitationally bound to you and to everything else, that perhaps there's these tiny little micro changes that happen in your birth that are specified by the position of the planet in the solar system and the planet with respect to all the other planets. And it's an interesting argument that's both broken but also has some promise. Because, just to give you some idea, Jupiter is the biggest planet in our solar system. Now, Jupiter is it's enormous, okay? It has a huge mass. But so that if you were standing on it here, you would feel squished. It doesn't really have a surface in the same way as the Earth, but it would smash you. Its gravity is so strong. But the effect of that gravity actually falls off with an inverse square of its distance from us. And so what happens is that if you move Jupiter to its present location, what you feel is something like 0.000000054 times the effect of the gravity that you would feel at Jupiter. So it's a very, very small effect of Jupiter's gravity on you. That being said, it does seem like there's something very real about the effect of all of the bodies on us at all times. So there's a concept in physics called inertia. This is the tendency of a body to stay in place or to stay in motion once it goes into motion. And one of the most important scientists who worked on this problem, his name was Ernst Mach. And we know him from the speeds, Mach 1, Mach 2. These are supersonic speeds. But Mach's principle was essentially something that helped Einstein come up with his mathematical rendition of the universe. But what Mach was really curious with was, how is it that, when you spin your arms, like I was saying earlier, why is it that my arms want to stay behind me when I spin my body? And what he surmised was that essentially my arms are being held in place by all of the other material in the universe is somehow holding everything in place. This is the basis of inertia. And so while I think that the astrological predictions from an objective mechanical perspective don't seem to play out, because I think that the effect of the gravity of an individual planet by itself is absolutely minuscule, it seems like there is an effect of all of the bodies in the universe, and they all really do seem to have a great deal of weight with respect to any individual body within it. All right, so to conclude all of this, and I will try to wrap this up very quickly. The culture defines essentially what people make of what they see. And for a very long time in the West, we had a very homogeneous culture, and we essentially had a church which gave us this explanation for how things work. It gave us a moral compass, right? And in some sense, this has been very tyrannical and very oppressive, and there's been great reasons for why people have moved away from these standardized religions in the last 100 years or so. And in some sense, that's been a real blessing, right? There's certainly less tyranny as a result of that. But in some sense, it's been a real disaster. And Nietzsche predicted this would happen. He said, in the absence of religion, people are going to have to become supermen. They're going to have to create their own religions for themselves. And you might think, well, that's a wonderful thing to create your own religion for yourself. But it's not entirely clear that it is such a wonderful thing, because out of that, you had these demagogues like Hitler that arose, right? Who decide that the religion looks like this, and they recruit people to follow them into these ways, right? So, if you have the ability to create your own set of values that are not the values of the entire culture as a homogeneous whole, you run the risk of coming into conflict with those values against other people. And so it's not entirely clear to me that the solution is that we adopt splintered ideas of what we value in the world, but more that we refine what is actually communally important to all of us. And I think that's what the ancient traditions were trying to do. They, of course, went off the rails in many instances. So anyways, that's some food for thought. And I want you guys to try to think a little bit deeper when you watch movies, watch those TV shows, and see what kind of mythology you can sense from our modern era. And I would love to hear your ideas from that. And we'll continue with the birth of modern astronomy next class. Thank you, guys.